Okay, you guys see my screen?
Yeah.
So I actually was going to look first at this issue, not this one. This issue that came up in the H5 forum, complaining that variable length strings take a lot of space on disk. So in H5 they got a lot of issues that turn out to be actually library issues. And this is one of those. It's not really a bug, it's just this observation. So I thought this was really actually clever, the guy's Python code. So he does, actually, let me switch to my HDF lab, because I have the same code here. So we'll start with use h5 equals 1. So we'll import h5 and use the current directory. And he, let me clear this. So he takes this, the quick brown fox jumps over the lazy dog, and he runs it through split to create an array with these words. So the quick brown fox jumps over the lazy dog. And then I haven't even come across this word, a numpy.random choice, 1 million. So it looks like this creates a NumPy array of 1 million elements, randomly picking one of these words. So there we have that. So we have 1 million element array, and the object type is object, because it's NumPy doesn't do variable length arrays, really. You just have an array of pointers to Python strings in this case. And here we're going to create a file called vLengthStrings none that basically creates a data set of variable length type and no compression. So we do that, and that took 600 milliseconds. And now we'll do the same thing using gzip compression. That took a little longer. And now we'll do the same thing using fixed length strings. So over here, what he does is another clever NumPy thing. Vectorize this to the max. I get the max length of every string in this million string array to get the max length, and then creates a fixed length string type of max length, and then creates a data set using that fixed length string type. Okay, that was pretty fast. And finally, the same thing with gzip compression. Okay, so here we are. Now, if we go look, ignore all that. Wrong place. So have here. So we have the fixed length string gzip was 654K. The uncompressed was for fixed length was 4.6 megabytes. And the gzipped variable length was 26 megabytes. And the uncompressed was 39 megabytes. So his issue was that the storage using the variable length strings was by a factor of 50 larger than fixed length strings. Okay, so back on the issue, Alexander responded that pretty fast and said, this is just how the library works. And we'll need some kind of library enhancement to deal with it. But then I was curious to do this with HSDS. So going back to here, if we change this to 0, now we're going to use H5PyD. And this, in H5PyD, you don't have such thing as relative paths. You always have to use absolute path. So /home/jread/doctor is the folder in HSDS that I'll use for this. And same stuff again. Okay, so all this same code works here. So we will create the variable length non-compressed version. And this takes quite a bit longer. And I was looking at the code for this. This was actually here. In Python, you want to avoid loops. And what we do in the H5PyD code is that we take this NumPy array, which is basically an array of pointers to things, and it gets compactified to this representation that we use in HSDS, which is the length of the element followed by the value of the element, followed by the length of the next element, followed by the value of that element, and so on. And what you have is then a contiguous stream of values that contains all the variable length data. But the thing I observed is that in Python, it's surprisingly fast as long as you rely on packages that are actually C code. So for example, here in this guy's code, doing things like np.random choice, that is actually calling compiled C code behind the scenes. And so it's really fast. If you did the same thing in a Python loop where you're iterating over 1 million elements, it's quite slow. And that's what we have here in the H5PyD code. It's nice that it takes this variable length NumPy array and converts it to this contiguous format that then we can then send in an HTTP request. But since it has to iterate through each of these elements, it's a little bit slow. And that's what we see here. That this took 15 seconds to create the data set with the 1 million elements. And I haven't deep dived into this, but I think most of the time was actually spent on the client side, converting that NumPy array to the byte stream. I see we have some late joiners here. We are discussing this issue. Variable length strings take a lot of space on disk. Let me put that in the chat. Actually, I don't know how to do chat. Is there a chatting? But anyway, it's here in H5Py 2152. And when we looked at this, the fixed length string version took either 4.8 megabytes uncompressed or 654 kilobytes compressed, whereas the variable length, basically the same data, took either 39 megabytes or 26 megabytes. So quite a huge jump in file size. And right now we're looking at this using HSDS and H5PyD. So let me continue on with this. Did I run this or not? Okay, so these were very fast for the fixed link, right? So a little slower than using H5Pi, but quite reasonable. This one took some time to run. Let me try this. Okay. Anyway, so now if we go look at these files on HSDS, we can't list them because they're on the server, but we can run HS, let me type, HSLS home ready doctor. So I have these files, and I'd like to see how big they are. And there's one thing I want to point out in a second. Ignore these two. So the V-link string with no compression took 7.5 megabytes. And the V-link string with compression took 909 kilobytes. So compare that with HI5, 26 and 39 megabytes. And now the fixed length string gzip and the fixed length string none took 0 bytes. Well, that wasn't some kind of magic. This the way that HSDS creates these summary information about total size of the domain is an asynchronous process. So it runs like a minute after the last update to the file. So let me see if it's all there now. Yeah, so now we have these two. So the fixed length string gzipped was 635 compared to 654, so almost exactly the same. And same thing for the uncompressed, 4.8 megabytes versus 4.08 megabytes on HDF5 library. So almost exactly the same storage for fixed length strings, but much less storage used for the variable length strings. And I think I'm not conversant in the details of how variable length arrays get stored in the library, but I think the way that it's working in HSDS, it's more amenable to compression and less verbose in general.
Mm-hmm. So John, a quick question. Do I understand correctly, you store length and string, right?
Right.
Have you tried to store just lengths and strings as two separate blobs and apply compression to separate thing? It probably will give you even better compression. And by the way, what you're doing, it is kind of in the proposal for reworking variable length strings in the HDF5. There is RFC from Quincy and John that related to variable length chunks and variable length data. Because what we're doing now, it's insane, right? As we see, for 39 megabytes. And I think we still should look what is going on, because essentially data is stored in those global heaps along with some other information. Plus in data sets, there are pointers to those heaps and some decode. So we're probably storing more information than needed. So it can be optimized, but it should be re-implemented. It's bad. You cannot subset in a nice way. You cannot compress. So this, and there's a proposal how to do it. So
okay, hopefully that'll get picked up.
Yeah, it's high priority for HDF5 2.0.
Yeah, so I think it'd be great if we could, well, if it's good, I mean, utilize the same kind of format that we use HSDS. And then we could do the same kind of trick where HSDS, so let me back up. So when you have HDF5 files stored, say, in S3, it's possible to load those in HSDS where you're not actually copying all the data in the HSDS native format, but you're copying the metadata, and then HSDS keeps track of where the chunks are in the original file. Now, this doesn't work in the case where the HDF5 file has variable length data, because obviously it's scattered all around the file, and it would be very inefficient for HSDFs to go and track down each of those elements. But if HDF5 library could store variable length chunks as a contiguous range of storage, then you could do the same kind of trick, right? You could have HSDFs looking at a contiguous set of data and pulling out the variable length strings as needed.
Right, and sizes can be part of that variable chunk information. So it's the same ideas with sparse chunks. So hopefully we'll be getting there.
Yeah, that'd be great.
Another, just for entertainment, John, if you have H5 stat installed, you can see on your local system what is the difference between metadata sizes and just raw data sizes in those files with variable length. And the metadata will be huge.
Yeah, I was about to point out. So this hsinfo command will tell you kind of the summary information. I guess it's very similar to what you're talking about for the library. So we have the owner, which is me, and the ID of the root group, the last modified time, the last scan time, the MD5 checksum, the total size, allocated bytes, and metadata bytes. So almost all the content are chunk data, and then just 814 bytes of metadata. 2 objects and 32 chunks in this file. All right. Okay. Any other further discussions or comments about variable length data? I can move on. I'd like to talk about this this blog that came out just this week, and yeah, I'm going to probably overstep my level of competence here in this blog. I want to talk about caching, and at first I talk about caching in the here. Let me share this blog. I figured out how to do chatting.
I'll put it in chat. You can just go.
Okay, all right. Okay, thanks, Lori. Anyway, so first I talk about caching, how it works in the HDF5 library. And I note that here's an example where I have, say, a data set that's 1024 by 256, or sorry, 5000 by 256, and my chunk layout is 1024 by 256. So if we kind of schematize this, you have a data set and up to 5 of these chunks, right? The chunks aren't actually allocated until the user writes to one of those chunks, but potentially you have 5 chunks in this data set. And in the library, there's a chunk cache. So the way a chunk cache works is that the first time a chunk is accessed, it gets loaded into the cache, and then it sits there for as long as you have a reference to that file open, and as long as that chunk has been evicted. So in our example, we iterate through all 5,000 rows of this data set. We read each row and then print the mean. So what happens is the first 1024 iterations, you're just reading chunk 0. And chunk 0 can fit in the cache. We go to iteration 1024, and then we'll have to read chunk 1. Okay, so it turns out by default, this chunk cache will just be large enough for 1 chunk. And so, but that's fine in this case, because as we go to chunk 1, we never need to go back to chunk 0. And it'll all be very fast until you get to chunk 2 and then so on. But then if we look at the code like this, where we're reading the data set by columns, there's going to be a problem, because you'll need all 5 chunks in each iteration of that loop. And by default, the chunk cache isn't large enough for 5 chunks. So it turns out in H5Pi, there is a parameter that you use at file open time. I'm a little unclear why it's file open time and not dataset reference time, but anyway, it's RDC n bytes. So this parameter you can supply in file open, and if you say 5 megabytes, you'll get a 5 megabyte chunk cache, and so on. And I was a little unclear, maybe Dana or Elena, you know, is this 5 megabytes for the entire file, or is it 5 megabytes per data set?
It is per data set, and this is size per data set per the whole file. That's why there is another API to set different sizes for cache for different data set. But this is where the danger is when you open a lot of data sets, right? Each of them will have this huge, and you will then be doing swapping memory. That's crazy. That's why it's really, this is another improvement we need to do, to have cache per many data sets.
Yeah, interesting. And I think in H5Pi, they don't have a data set parameter to set the chunk cache per data set.
It's different API in HDF5.
Yeah. So, so that's caching. So and there's even more details, even more esoteric ways to modify the chunk cache behavior in the library, which I didn't get into. And then we're talking about caching in HSDS. So let me go to another example just to illustrate this. So this is my favorite NREL example. So let's go here, this version. And here we're going to open this data set. It's actually, this bucket is owned by National Renewable Energy Lab, which is good because we couldn't afford to pay the storage fees on it. And it's a bunch of data sets. We'll get one data set, has an ID, has a shape, has a type, has a chunk layout. And the data set basically is 1 terabyte per data set, so a fairly large data set. Now, the chunk layout, recall, is 24. So let me go to something like 45. And this is a magic number, you'll see right. And I'm going to read this top slice of this data set. So we do that. That took 698 milliseconds. And then I can make a nice plot of that. Okay. Now, if I go and read this again, my hypothesis is that HSDS has already loaded this chunk in the server chunk cache, and the time will be much faster the second time through. So let's do that. And my assumption was totally wrong. Let me try something. You must have read that before. Let me say 2. Just picking a random number here. Read a slice. Okay, this is more like it. So this took 3.5 seconds to read this slice. So from my session here, request went out to HSDS. HSDS figured out which chunks are needed to read the slice. And then it started talking to S3 to read these chunks from the S3 storage system. It got those chunks back and then sent the requested data back to the notebook, and then we can display it like that. Okay, now second time through, let's cross our fingers, this should be faster. So it went from 3.46 seconds to 598 milliseconds, right? So like 7 times faster, 5 times faster the second time through. Because the second time, the server didn't need to go to S3, it already had this cache data. And if I change this to be another slice, even though it's a different slice, it's still in the chunk cache. right? Because we haven't crossed the chunk boundary. And what's going to happen, I believe, is as we get crossing the boundary, we will have another slowdown right about here. See, so that took 3.28 seconds, and then we'll get another speed up. All right, and so just talking about how the chunk cache works in HSDS. So HSDS is a set of these containers, the service nodes and data nodes. The data nodes partition the object storage. So here are all the objects that comprise a domain, and each data node owns one partition. And that means that if a data node has to, say, read from S3, it can load that. And it can keep that in its metadata or chunk cache as long as there's room in the cache, just like with the library. And how much room is determined by this configuration parameter in the server. So it defaults to 128 megabytes for chunk cache and for metadata cache. But you can set that to be anything you want, 10 gigabytes, assuming you have memory on your server for that. But the other thing is that the total size of the cache scales to a number of these data nodes, because each data node by default would have its 128 megabyte cache, right? So if I'm running 4, I would have 128 times 4 be half gigabyte. If I was running 8, I'd have 1 gigabyte of chunk cache, totally. So by running a large enough set of containers or running on Kubernetes, you can have quite a large amount of memory that's available for much faster access than going to storage. Of course, you have to kind of warm that data up by accessing it once so that it moves to the chunk cache, but future access is much faster. All right. And then I was going to talk about caching in H5PyD. So in H5PyD, there's no equivalent of a chunk cache because chunks live on the server, and H5PyD just requests selections of data sets. But there is a metadata cache, and I can illustrate how this works. Which is here. So So we're going to open this file called smallobject10.h5. And we list that. Okay, so this thing has maybe it has 20 groups. Okay, 20 groups, some data sets, and so on. And now there's a parameter on H5PyD file open called use cache. And that defaults to true. And what it does is when you open the file, it reads all the metadata for that file in one request. So here, when you do file open, it's doing a get domain to the server. And there's a parameter here that says, bring all the JSON data for this domain back to the client. And that gets stored in this metadata cache. And the result is when a client is trying to list links in a group or get a data set, shape, or view attributes, it's all there in memory. And we can see how this works. So if I have, if I want to get this group G005 child 2. I can do that. And it took a speedy 82.5 microseconds, right? Because it didn't have to go to the server. And there's the group. And I can print all the group attributes. And that took 394 microseconds. And then here is, we're going to do a iteration through all the objects in the file, this f.visitItems, which calls here. And we're going to create a count of number of attributes, number of groups, number of data sets. So we come here. If the object ID starts with G, it's a group. I add the group count. If it's data set, I add to the data set count. If it's an attribute, I add the number of attributes in that object. And they run pretty fast, 5 milliseconds, and we have a total of 240 attributes, 101 groups, and 41 data sets. Okay, so that was all with this use cache equals true, right? So let's set it to false and see what happens. So this file open took 182 milliseconds before, and now it took 14 milliseconds. So quite a bit faster to open the file because the server didn't have to iterate through all these objects and return the big blob of JSON back to H5PyD. But that's a happy case, right? The downside is we reference a group, this will take a bit longer. So 24 milliseconds, so 1,000 times longer to access this particular group, because now we have to go from the client to the server and back to get that information. And it's all the same data. And this too, iterating through the attributes took longer than before. And with my visit function, this will take quite a bit longer, 2 seconds. So all in all, you might say, why don't we always have use cache be true? Well, there's a limit that's configured on the server of how much is too much. Right? If I list this other file I have, a small object, oops. So here's a domain that has about 100 objects. Okay, and if I go through this one, I'll say use cache to be true. It took, it was suspiciously fast. And if I reference a group in this new domain, it takes quite a long time, right? So now I can go back, say, to 99. And the reason is that even though we set use cache to be true, there's configuration that says if the amount of metadata is beyond a certain limit, I think it's like a couple of megabytes, then we don't load all the metadata, right? Because we didn't want to take a exceedingly long time for files that had multi-megabytes of metadata. So here you're actually reverting to the same behavior as use cache equals false. All right, that's a little tidbit to know. And the final thing I talked about in the blog was web caching. So here's this idea of, imagine I have a client and my client is, say, on my workstation in an institution. And I have HSDS running somewhere else. Let's say it's running in the Amazon data center. It's a quite a long round trip, right? From my workstation to the server and back. So in this circumstance, it may make sense to create what's called a web cache. You create a proxy at your institution. So you have fast connectivity from the client to the proxy. And then from the proxy, it forwards all requests to HSDS, which is in the far away location. And why do this? Well, the proxy can save request, and next time that same request comes, it returns the response it's saved, right? So it's another form of caching. And so if you have a lot of requests that are repeating, you'll save this time of making the request all the way to server and back again, right? So for example, if I take this link, so here we have HSDS, HDF Lab, the HDF Group, or datasets, a dataset UID, a value, right, and this domain. So this is REST request is saying, give me all the values for this particular dataset in that domain. And I can click on it here, and voila, we got these, right? Well, that didn't take very long, even though I am running this on my notebook, and it did go all the way to Amazon and back. But if you had requests, either a lot of requests or requests that read a lot of data, you could save a lot of time by having this proxy set up. Okay, and I think that's all I have to say about caching. Do we have any comments on this or other questions? I think I lost most of my audience, but anyway. So Laurie, do you have any other questions?
Well, I don't have questions.
I mean,
No.
and on chat or anything?
Yeah, well, next week it will be Scott Breitenfeld, who is our Fortran and HPC person. So tune in next week. We also have a webinar that I've announced on the forum, so you can jump on there and register for that coming up October 26th. So
awesome.
Thank you, everyone, and we'll see you here next week.
All right. Okay. Bye, guys.